Go ahead.
Thank you very much, Sandro, and may I thank you again for the invitation here and being so kind while I am here. And I'm going to show off by saying he's been so kind that he's going to set up an experiment looking at the theoretical calculations I gave yesterday. Now I'm doing 5 lectures, so there are 5 experiments to come, and I look forward to all of it. And there is one associated with this subject of lava flows, but something's happened to the first slide. I don't know why. It wasn't as I saw it when I last put it in, but it's going to talk about lava flows and defending lives and housing by theory, experiments and field data, and somehow it's got muddled up, and I hope my talk won't get as muddled up as this. But what I would like to say to the audience here and also to the online audience, please do interrupt and ask questions. Let me be aware of your thoughts, even if they say we disagree with you. That'll be an interesting way to start a discussion. Well, what I'm going to do is give you an introduction to lava flows, tell you something about the mathematics, then show you how we have done some experimental confirmation, a little bit about the field data, and then what I hope you'll take from this. There are lots of different geometries that you can consider. Topography plays a very large role in lava flows. The first thing, just to get some feeling, is to consider one-dimensional topography. In other words, it doesn't vary at right angles to the way the flow is taking place. It seems that nobody can hear me. I'm talking to myself.
Okay, go ahead.
Right, I can talk now, you can hear me. So there are different geometries and consequences. The simplest one is one-dimensional, where the flow just goes down a slope and reaches this topography, and it must go over it. There's nothing else that it can do. On the other hand, it can pond, it can stay and be caught by the topography. Then there are situations where you have axisymmetric topography, starting with relatively easy, and then there's the question to ask, when does it get to the top of the topography and cover it all, and when does it not? When does it form dry patches that are safe for people to stand in, and how big they are? Then we'll talk about some experiments we've done, easiest in the lab, of a tall cylinder as the topography. But it's interesting, as you'll see, when there are dry patches where it would be safe to stand, and very few houses are really infinitely tall cylinders, but as you'll see, it gives us some indication, because there are some structures that are big enough to withstand lava flowing over them, but not necessarily to stop lava bringing them down, destroying them totally. Then I'll tell you about a long defensive wall, and that's important, a barrier to stop the lava coming onto a home or a city, and I'll calculate the maximal force. And then I'll tell you about depressions, because real topography has both elevations and depressions, and so we've looked at both of them. Here's some simple steady flow examples. We start in A with a line source. As you see at the top of the incline, it goes down and it meets this topography that you see in A. And now 2 things more or less can happen. One is shown in B, where the lava flows over all the topography, and the other is as shown in C, where the topography is sufficiently high that the lava doesn't have enough energy effectively potential energy, to go over it. And you see a sort of a sketch in the second part of B and the second part of C, which also says how we're going to relate matters. So the topography is going to be related by D, and it'll be a function of X, which is down the slope, and Y across the slope, and the thickness of the flow by capital H, which will also be a function of across the slope and down the slope when it's two-dimensional. But you can have situations, as you see on the bottom right hand, where the topography is sufficiently high that the lava flow doesn't get to the top and it has to go around it. Now, to get some scaling, if you have a constant flux per unit width, then the thickness of the flow is given by this expression involving the flux Q, the dynamic viscosity mu, the difference in density between the lava and the air on top of it, but basically that's just the density of the lava, gravity, and the sine of the angle of the topography. And of course what happens in real lava flows is that there's a slowly varying change in the flux, and so this is correct. And I've shown in the bottom in pink more or less what all the variables are. Now we non-dimensionalize with respect to some length scale capital L, that is the horizontal length scale in X and Y. In Z we non-dimensionalize by the height of, or the thickness of the flow at as it's flowing down, initiated, and then non-dimensionalized time. And this gives us these two equations, equations of motion, if you like, that involve two parameters. And I'll say rather softly, I'm sorry that those parameters are curly f and curly m. They were introduced by my summer student. They're not the ones I would have used, but curly f is a non-dimensional indication of the height of the topography. And I always remember that as fire hose, it's telling you the height. Curly f is h infinity over the horizontal length scale times the tan of the angle. And then m, which I always remember as medical doctor, because it's the width of the topography divided by the angle. Basically the slope, d over l, divided by tan beta. Anyhow, if we have a two-dimensional situation that's independent of time, just so we get some feeling, this is the equation that we need to solve. Now, it's non-linear, but these days that's not so bad. And what can happen, and this is really of greatest interest, is that either the flow can be at the bottom left if the script m is less than some critical value of given by MC, or it can be greater and then it ponds. The barrier keeps back some of it, not all of it, because what's originated the line source has to, in the end, go all the way downstream in a two-dimensional situation. But these are interesting possibilities. But let's go on to consider more realistic three-dimensional topography, where the topography, the mountain, non-dimensionalized, m is just a exponential of minus r squared, so it's a Gaussian in radius. And here are just two values of the f and the m. and showing you the difference. In the top one, you see everything is overflown by the lava, and the thickest it is 1.18. The height of the topography is 0.5. On the other hand, if you make a greater height with the same flux, then you have a dry zone, because on that greater height it just can't get over it. And not only do you have a dry zone, as indicated there, with H equal to 0 over that reasonably large region, but of course, where it's at its thickest, it's thicker than if there was a smaller height, because the lava has been diverted, and you see here it's 30-40% thicker with greater height. This now shows you more or less a distribution. It's a relatively small topographic hill, and you see now how the lava gets stopped by the hill, but far off, of course, the hill doesn't affect it at all. Now, what happens if we make the topography a cylinder, because that's going to be easy to do in the laboratory and also gives you some indication. But you can have different values of F. In other words, different values of the flow upstream. If F is 20, or curly F is 20, then it's quite thick and going quite rapidly, and there's nothing really spectacular. But as you decrease F, as you see for F equals 1, the flow pattern is rather different. And when you decrease F sufficiently, again, there'll be a separation from this flow, and you'll have a dry zone. You can't have overtopping or not overtopping, because this is a cylinder, which I'll show you in the lab in a minute, but it indicates when there's a dry zone. And that's one of the things that you really want to know. A, when will there be a dry zone? B, can you build houses so that there'll be a dry zone behind them, or what sort of topography or barriers, as we'll see. This is now a experiment that we did. The lava was a viscous fluid. It came down, it met this cylinder, and this is at some stage after the flow has gone partly past the cylinder. But you see there's a separation and there's a dry zone. The force on the cylinder, that's a standard business. I won't go into the details here, but you can calculate the force. And this has been published, so you could look this up. This is the maximum and minimum depths, both upstream or downstream, depending upon the script F, but really that's the thickness or rapidity of the flow that's introduced. And we can solve the equations asymptotically, which one always likes to do, or at least old people like me like to do. Youngsters prefer numerical solutions. They can do that more quickly. And you see the asymptotic predictions with dotted lines agree quite well once the flow has got to be quite thick with the numerical calculations. And theta equals 0 is the oncoming angle, and theta equals pi is exactly behind it. These are now some experiments, and you see how the theory and the experiments agree quite well. And I might just say, I've never heard anybody give a seminar where they've said the theory and the experiment didn't agree at all. That's the only point of talking about it. Now, what about a square obstacle? Well, here again we can do numerical calculations, and you see what a difference the flow field looks like depending on the curly f, i.e. When f is large, that's a large h infinity, it means a large velocity of flow. And then being a square cylinder or a round cylinder is not much different. But once you have a rather slow flow, f is 0.25, you see it is really very different. And that already tells you that under some useful conditions, that the shape of the topography or the shape of the obstacle, because we have in mind houses and things like that, will play a large role. Now, what about a differently related object? It's still a square, but it's been rotated by 45 degrees, and of course there's a symmetry, so it's really almost a triangle, but it's a triangle with the apex at right angles to the flow, and that looks quite different for this value of f. I could tell you lots and lots of things. And you can evaluate the force reasonably straightforwardly. Now, there are a number of further questions. What shape of cross-sectional area has the largest dry zone? Now, if you want to build a building, you might decide to have it circular or square or rectangular. And how does this depend on the input parameters? And let me say rather loudly, this is an interesting theoretical calculation, numerical calculation, and an experiment that hasn't been done. That's why I'm saying it loudly. So, can you think of anybody who might be able to do that? It's the theory can be done, I think, by a good, even undergraduate student, and the experiment would be great fun. And I've been lucky coming here to Italy, having found a really wonderful experimental guy, and so that should go. Now, here we look at elliptical topography because I wanted to stretch it out and look what happens if you have a wall, which you can describe by making B very large. Okay. And now you can calculate the force just as it's on the verge of overtopping. And so for typical values, the force on the wall, if it's just about to go, is 10 to the 7th newtons per meter. And what I like about this slide is I presented this talk in a country, and I'm not going to even mention the country, that has considerable volcanic activity, and at the place that was the head of the group defending the country against these lava flows. And my host, who was very nice to me, when I got to this, he said out loudly, calculating the force. I would have never thought of that. That's so important, such a good idea, calculating the force. And I thought, but I didn't say, because I'm a well-mannered man, if you had thought of it, I don't believe you would have known how to do the calculation anyhow. But I didn't say that. I, at about the same time, went on a hike in northern Scotland, and there was this sign here, danger. Unsafe walls. Proceed at your own risk. I didn't have the slightest idea what was unsafe. There were no volcanic eruptions now. There were some time ago in Scotland, and there was no water, but I just liked it. This is a slide that was lent to me from the woman who's in charge of barrier design in Iceland, and I'll tell you a little bit more about the work that I've done with her. But the Icelanders are enormously quick in building barriers and defending against lava flows. It's most impressive. And unlike this slide, where this is a very important power antenna, and they've built quite a high barrier, in effect, to protect it if there are lava flows, and as I'll show you in a minute, there are. And they've also protected the road by putting a barrier next to it. But that leads you to questions of how big does the barrier have to be? But that, of course, also depends on the unknown volume flow. You don't know, you know what the flows were in the past, but new eruption might be different. Now, of course, topography has not only highs, but it also has lows, and so we've looked at flow not over a topographic high, but a topographic low like this, and they are really quite different, and the reason that they're different is that they can constrain or collect the flow into them, whereas a positive topography pushes it aside, a negative topography brings it in, and that makes a difference even to the flow pattern downstream of the topography. And here you see the difference between a topographic high on the left and a topographic low on the right. The topographic high on the left diverts the flow, and so it's at its largest about two topographies away, two topographic length scales away. Whereas if it's a depression, then there's a considerable decrease in the flow somewhat downstream because the flow is taken into the depression. Well, of course, having done a large topography and negative topography, I had to do one of both, and this just shows the difference. In one case, it's a negative topography, a negative Gaussian followed by a positive Gaussian, and the difference if they're in the other order. This again just shows a few things, but I think we might talk now about some older volcanic eruptions of McCarth in South Texas, and I've just forgotten how many years ago it was. Older than me, 2,000 or 2,500 or something. That is older than me, and I'll show you how our calculations are. Well, this is the calculations using the topography of how the lava would have flowed. You see where the vent is, and it would have taken, we calculate, something like 4 or 5 days to have got to the bottom. There was no one around in those days, so everybody was safe, but it gives you some indication of what we calculated would have been like. And so you see here now the pictures at various time, and whoops, and it's in good agreement with what is now seen. Now, somebody said to me during a talk, I think it was, that my calculations are with constant viscosity, but viscosity tends to change as the lava flows, and that was a question during a seminar, and I said, well, I don't think that makes much difference, and he more or less said, I don't believe you. He said it politely, but that's what he did. So I decided to do at least 3 calculations where I said the viscosity doesn't change with time at all. That's one. Number 2, it changes quite quickly within an hour to get to its final value, and 3 takes much longer. And according to my questioner, that would have made a difference, but here they are, the 2 different sorts, and there's not much difference. You see that the amount of lava is really the same. Then there's the question of what about if it spatially varies rather than temporally varies. And here you see from a vent it can either be constant or it can increase over 200 meters from the vent. And again, there's not much difference. Now, of course, general topography is not made up of just one axisymmetric case, but it's really rough, as you've seen here. But I think you can learn a lot from understanding what happens from isolated topography to real topography, as you see here. Now, as I said, I've been involved quite a bit in the Icelandic eruption. And there's a woman there, an engineer, who's responsible for the barriers, who I think is wonderful. And I've done quite a bit of work with her and been impressed by what they can do. And this is the problem in 2023, so reasonably recently, 2 years ago. And time is along the screen, some 4 days, and you see how it's going down and expanding. Now, this was looking at our topographic calculations, in that the black line, or the black curve, it's far from a line, is what the topography that was measured long before the eruption. And then after the eruption, you see the blue topography with lots of little jiggles in it, because the resultant topography has little rocks and things like that, and that we don't take into account in our calculations, all nice, smooth. But we got the red smooth curve, which agrees quite well with the observations, and the next lava flow will go over the red curve, and we'll no doubt make some more calculations. This is Grindavik, which I read recently is the most dangerous place in the world due to lava flows. And this is an eruption in 24, and it came down and really was almost ready to flow over the whole town, and people were understandably very worried about it. And in the end, you see in red the actual lava depth, and in white our calculation. Not perfect, but it seems to me not bad. So what I want to say to you is that the lava flows can be calculated numerically, and there are some useful limits that give you some understanding. Two-dimensional, axisymmetric, long walls. The agreement with some special laboratory experiments look very good. With further experiments to be undertaken, there are really some fascinating questions about what's the difference between an elongated rectangle facing the flow, or an elongated rectangle at right angles to the flow, and it may play a role in how you build a house. And I was going to show a video, but I guess I forgot to include it, that I was shown a few months ago of a lava flow gradually coming to a house. It came into a house so slowly that all the occupants left. But then the video wonderfully shows, well, I think wonderfully, how the house basically gets destroyed by the flow. So when I was shown this video some 2 months ago, I of course immediately put my hand up and said, what if the house had been built at right angles to how it was? Well, of course, the person who showed the real video had no idea. And then this tells you something about me. I put here, agreement with field data is fantastic. That's a little arrogant, but it's not bad. Here are some references of what we've written in the various things. And with that, I think I will just introduce you to the people who've helped me. I'm going to start with Jack Saville, who was a summer student, an undergraduate who worked with me. Ed Hinton, who's now a professor in Melbourne, but he was a summer student also, but a graduate summer student at Woods Hole. And if I just have enough time to tell you, Ed and I got on very well, and then he said one day, I'm getting married in a few weeks' time. I said, oh, I'd love to meet your future wife. And he said, oh, well, we'll have to see what we can arrange. And I said, oh, look, how about I take you both to King's, which is the background to this photograph, for dinner, okay? So it was agreed, and I was waiting outside King's, and along came Ed. I could see him at a straight road there, maybe 400 meters from our meeting place. I could see him touch his wife-to-be and point towards me, and she seemed to become excited by that statement. And then as she came closer and closer to me, she clearly got more excited about meeting me. And I thought, what's going on here? I've never met you before. Why are you so... And then when she finally came up to me, and Ed hardly had been able to say, this is her, but she put out her hand with enthusiasm and said, I wanted to meet you for such a long time because you lectured to my father when he was an undergraduate, which made me feel very young. And Andrew Hogg, an old time graduate student of mine, but now a professor in Bristol, also helped, and I'm very grateful to them. Also, I've become interested in geology some 30, 40 years ago due to Steve Sparks, who's a wonderful guy and a fabulous, one of the world's best geologists. And it was an interesting, and I say this on purpose, interesting interaction in that he's one of the world's best geologists, and he really knows very little fluid mechanics, very little indeed, and little mathematics also. That's unfair to say he knows little fluid mechanics. He has a feeling for it, there's no doubt about it, but mathematics he can't do. And I, of course, don't know any geology, so we got on very well, and we initiated this field of geological fluid mechanics, to which we both